So let's take a look at the evidence favoring the network approach. Hints are a big factor here. Hints help us according to the network approach because they spread activation to the correct node. So let's say that you at one point learned that South Dakota's capital is Pierre. You are trying to remember it and you're having trouble. Now someone gives you a hint, and that hint is, it's a man's name. Well, that helps because now in your memory, we have activated information or nodes in the networks related to, say, South Dakota, but also related to it's a man's name. And so because of spreading activation, information spreads out along all the different nodes related to different men's names, including Pierre, as well as the spreading information from the nodes related to what you know about South Dakota. So even though you don't at the moment recall that Pierre is the capital of South Dakota, you do have that in your memory. And so the hint, hey, it's a man's name, sends spreading activation to Pierre, which is also connected to your knowledge of South Dakota, and voila. Because you're spreading activation now from two different nodes, we're able to activate this concept here, this node with the name Pierre, and allow us to remember, aha, that is the capital of South Dakota. So let's take a look at the evidence favoring the network approach. Networks also suggest an explanation for something called state-dependent learning. During learning, connections are strengthened between the context we're in and the learned material. So if you've ever heard that it's better to take a test in the same classroom where you study the material, or it's better to study in the library because maybe the environment is a little more similar to the classroom environment where you would be tested, that's referring to an effect called state-dependent learning. So yes, there are these benefits for being tested in the same environment because the context itself can become a type of retrieval cue. If you're in the same context during testing, the learned material will receive pre-activation from those connections. Similarly, you may have had this experience just with a person. So if you've ever recognized a person very easily in one setting where you see them all the time, like the restaurant where they work, but you do not recognize the same person in a different setting, like if you happen to see them one day at the doctor's office, and you're looking at them and you're going, oh my gosh, okay, I know this face, it's very familiar, but you cannot remember their name, you cannot place where you even know them. That would be an example of state-dependent learning. When you go to the restaurant, it activates all the knowledge about the restaurant, including, hey, I'm expecting to see so-and-so who normally works at this restaurant. But if you see them all of a sudden unexpectedly at the doctor's office is not a place you've ever seen them before. There's no pre-activation. You do not expect to see them. And sure enough, it's really hard for you to remember who they are and what their name is. Other evidence for network models comes from what's called the sentence verification task. Just like it sounds like, it's where you're asked to verify whether a sentence is true or false. Participants just have to quickly decide whether sentences like the following are true, yes or no. Robins are birds, robins are animals, cats have hearts, cats are birds. So we have yes, 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 and no, right? So cats are not birds. So if we're going to confirm that cats have hearts, for example, we can look at how this information would be organized in Gillian's hierarchical model. So here we have a cat node, right? Information about hearts is a couple of links away. You have to go from the cat node to animals and then go to the information that's connected and true for all animals. So cats are animals and animals have hearts. So yes, to answer that cats have hearts and say yes in affirmative, cats do have hearts, you have to go from this node to the next node and then here. So 2 links. In contrast, to answer is a robin a bird, you can see that that's just 1 link away. So you should be able to answer that just a little bit more quickly. And so this type of research basically measures how long it takes people to come up with the answer. And they would expect it would take them just a little bit less time to answer a question that's really close together in this network versus answering a question that makes them travel to more distant nodes through the network. And the evidence does seem to confirm that information is organized in this way. So in terms of properties about, say, a canary, can it sing, can it fly, does it have skin, these different characteristics, it does seem that as we go further and further away from the canary node, it does take people just a little bit longer to answer that question. Same thing if we're asking about, which category a canary belongs to. Is a canary a canary? Is a canary a bird? Is a canary an animal? So it generally takes a little bit longer to answer a question about information that's further away in that network. So that's kind of encouraging that there's support for the network approach and that we do seem to kind of have to search our networks for this information, and if a node with knowledge that we need is a little bit further away, that we might take a little bit longer to get there and to retrieve that information. However, some evidence actually contradicts network theories. It turns out that it takes longer to verify that a chimpanzee is a primate than a chimpanzee is an animal. Makes no sense. If we think of the hierarchical model, chimpanzee should be here, primate, and then animal. It should take longer to confirm that a chimpanzee is an animal versus a primate, and yet it doesn't, right? So it's just kind of a weird difference. So the primate information is only one level away, while the animal information is 2 levels. Animal should take longer. It actually takes less time. But that does seem to contradict network theories. Other evidence that contradicts network theories is what's called the typicality effect. Now look at this very handsome bird right here. This is an ostrich. It's a bird, but it's not a typical bird. And so it's easier and faster for people to answer questions related to whether a canary is a bird versus whether this ostrich or an ostrich is a bird. Similarly, we can think of another atypical type of bird, here in this case a penguin, that would also take them a little bit longer to answer as opposed to, say, a canary or a robin. So these atypical birds do slow people down. However, in terms of the hierarchical model, they are at the same level as typical birds like canaries and robins. And so this is just not consistent. The fact that people don't answer questions as quickly about these unusual or less common type birds is sort of a problem for network theories, because they do not account for that at all. They just say knowledge is organized in this, big hierarchy. And that's the only way that's organized, and that's the only thing that should matter. And yet we see here that no, typicality also matters. So to summarize, we have supporting results here on the left in green. The semantic distance effect, basically that it takes less time to answer questions that are fewer levels away than questions that access information that are more levels away. The other piece of information is the repeated path hypothesis, where if you practice, for example, repeat an answer, you get faster at it. So we didn't talk about that, but that's just another thing that I'm sure we've all experienced. If you practice retrieving information, you get faster at it, which is why studying for our test is so helpful, right? So we practice coming up with the answers, and that will help us come up with the answer more quickly on the day of the final. So these two types of findings are definitely consistent with network theory, and in particular Killian's network theory, which organizes everything in a hierarchy. But remember, we have conflicting results from typicality effects. So since not all birds are as typical, like ostriches and penguins, according to network theory, should be able to access information about ostriches and penguins just as quickly as robins, but we can't. So there's something about atypical unusual type examples that shows us that there's more to how knowledge is organized than just network theory. So because of these conflicting results, we'll see, there are a variety of different network models. We focused on this one, Killian's, that organizes everything in a hierarchy. None of them are perfect, but this one's a nice example of how a network model works.